Last month, John Tomaszewski gave his talk on the James Webb Space Telescope Part 1. That talk covered its intended research mission, the technology involved to accomplish that, the temperature differences between the sun and solar panel side, the cold infrared scope side, and how the temperature difference is maintained. The talk also covered how it will help astrophysicists look further back in time to about 200,000 years before the Big Bang, when the universe just consisted of just plasma, hydrogen, and helium nuclei plus electrons, before it settled into atoms that allowed stars to form. Our speaker today for the math interest group is John Michejda. He's giving a talk on James Webb Space Telescope Part 2. He will cover the Lagrangian point system within the framework of classical Newtonian mechanics and how to keep the James Webb Telescope in its intended position. When I took freshman and sophomore physics, the professor mentioned that the Newtonian laws of mechanics only cover the two-body problem. For more bodies than that, the solution is not analytically solvable. Much later, I heard about the Lagrangian points with reference to the Jupiter-Sun system. These points in space where forces were at a minimum, and one could park a satellite in that space and easily keep it there. How do they calculate where these points are? Why do they work? I'm happy to say that John Michejda did some nice research into Lagrangian points and has put together a very nice set of slides explaining the concept and referenced that to existing telescope that includes the James Webb Telescope that's used in the Earth, Moon, Sun orbital domain. John has given a number of talks for MIG before, greenhouse gases that talked about which gases are greenhouse gases and why, vibrational modes versus temperatures in CO2 lasers, and now Lagrangian point systems with reference to the James Webb Telescope. So please welcome John in giving his MIG talk on the James Webb Space Telescope Part 2.
Okay, do you see the screen?
Everything looks good.
Okay, good. As Walt mentioned, this is a part 2 on James Webb Telescope. In this particular presentation, we will concentrate mostly on the orbits of the James Webb Telescope, and this is where we will talk about the Lagrangian points and so forth. I would like to point out that this talk will end with a 15-minute video, which is a video by the same fellow that gave me a very successful video presentation in John Tomaszewski's talk. The talk itself will probably last about an hour and 5 hours and 10 minutes. So the whole thing will take place, the whole thing will be about an hour and 25 minutes, just so you know. Okay, this is the outline of the talk. Basically, we will start with comparing the orbits of the James Webb Telescope with that of the Hubble Telescope. And what we will show you basically that the Hubble Telescope, its orbit is influenced mainly by the gravity of the Earth, while in Webb Telescope, it is the gravity of the sun that dominates it, but the gravity of the Earth is also significant. So Hubble can be considered to be a two-body problem, and a Webb Telescope will be considered to be three-body problem. When we talk about three-body problem, we will talk about Lagrange points, define what they are, and there are 5 Lagrange points altogether. We will calculate position of Lagrange point L2, which is where the Webb Telescope resides, or circles around that point. We also make a derivation of a position of L4 and L5. It's a complicated mathematical problem, but actually it turns out that you can find an analytical solution for it. Now, when I talk about stability of Lagrange points, I am talking about what happens when you place an object in Lagrange point and that object at some point gets perturbed. Will it come back to the Lagrange point, or will it just go away and go into the oblivion? So that discussion will talk about stability of Lagrange points of all of them. And then we'll switch gears to talk about the Webb telescope orbit. We'll talk about the environmental requirements of the Webb telescope, its architecture. We will make case for the Lagrange point L2, which is what NASA has chosen to be the point of orbit for the Webb telescope. And we'll discuss the halo orbit of Webb telescope around L2. And we will complete with the video, How James Webb Orbits Nothing by Christian Reddy. So without further ado, let's start with the two-body problems of Hubble and three-body problem of Webb telescope. So the distance between the Hubble telescope and Earth is about 570 kilometers. I should point out that's between the surface of the Earth. The distance between the Moon and the Earth is about 384,400 kilometers. And the distance between the Webb telescope and the Earth is 1.5 million kilometers. So it's way out in the space, much further than the Moon. As a reference, we also point out that we like to point out that the distance between the Earth and the Sun is 150 million kilometers. It's 1 astronomical unit. So one could ask a question: why is Webb telescope so far in space? It is really 1% of the distance between Earth and the Sun. It's 2,600 times further from the Earth than the Hubble, and it's 4 times further from the Earth than the Moon. It's really far. Well, in order to answer that question, we have to look at the mission of Hubble and mission of the Webb telescope. Hubble is a visible light and ultraviolet telescope. It does not sense infrared, and its sensitivity depends mainly on the sensitivity of its photodetectors and the background light noise, which is basically the ambient light. Its sensitivity is not affected by its temperature. So Hubble operates at relatively constant temperature of about 21 degrees C. For those who are not familiar with centigrade, 21 degrees C is, I think, about 68 degrees Fahrenheit. The Webb is an infrared telescope, and it senses heat, and it's designed to sense minute amounts of heat in space. So its sensitivity is critically dependent on the ambient temperature, since any residual heat in the telescope will be sensed as a signal and would be basically with the raised noise floor of infrared detectors. Because of that, the Webb operates at 45 degrees Kelvin, which is pretty cold. It's minus 228 degrees centigrade or minus 380 degrees Fahrenheit. I would like to point out that actually the sensors, the infrared sensors of the Webb telescope operate closer to 5 degrees Kelvin, which is fairly close to the absolute zero. So, because of its low temperature requirements, the Webb's orbits must be far away from the sources on infrared radiation. Well, such sources would be Earth, the Sun, and Moon, or any other planet in our solar system. This is why Webb operates 2,600 times further than Hubble, way out in space. However, because it operates at 1.5 million kilometers from the Earth. However, because it operates so far from the Earth gravitational force is much weaker than it would have been for Hubble, and Sun's gravitational force is very significant. So what we will do next is try to estimate what are the sort of ratios of the gravitational pulls from the Earth and the Sun, both for the Webb telescope and for the Hubble telescope. And to do so, we'll use Newton's law of universal gravitation. That law states that the force of attraction between two objects which have mass m1 and m2 is equal to a gravitational constant times the product of the two masses divided by the square of a distance between center of gravity of these two masses. Now let's imagine that we have a satellite with a mass m prime, placed distance re from the center of the Earth and distance rs from the center of the Sun. We know all of these. We know the magnitude. We know the weight of the Sun, the mass of the Sun, the mass of the Earth. We know the distance between the Sun and the Earth. So we can calculate now the ratio between gravitational forces of the Earth, Fe, and the Sun, Fs, on the satellite at any arbitrary point of space. And that ratio is basically using the Newton's formula. We have, this is essentially Newton's formula for the gravitational pull of the Earth, where m is lowercase m is the mass of the Earth, lowercase m prime is the mass of the satellite, divided by distance between the satellite and the center of the Earth. And we can also calculate what the pull of the Sun is on a satellite. The difference here is that we are using different distance. We're using distance between the center of the Sun to the m prime, and we're using product of the mass of the Sun times m prime. So we can simplify this equation by getting rid of the gravitational constants and also m primes. And we get this formula. We can plug in now the values of the mass of the Earth, which is about 6 times 10 to the 24th kilograms, divided by mass of the Sun, which is about 2 times 10 to the 30th kilograms. And it's also proportional to the ratio of the square of the ratio of the distance between the satellite and the Sun and the satellite and the Earth. When we cross multiply these numbers, we get this kind of relationship. It's 3 times 10 to minus 6 multiplied by square of the ratio of distance of the Sun to distance of the Earth. So now we can compute what this would look like for Hubble, that ratio would look like for Hubble, and what it would look like for the Webb telescope. On the top of this view graph, I just basically repeat the formula from the previous graph. But for Hubble telescope, we have a distance. Hubble telescope orbits about 570 kilometers above the Earth's surface, but the distance to the center of gravity of the Earth is much larger, because the Earth has about 6,400 kilometer radius. So when we add this distance to the 570 kilometers, we get about 7,000 kilometers from the center of the Earth. So given this, we can now compute what the ratio of the distances is. And we get that the ratio of the gravitational pulls is. And we find out that for Hubble, the gravitational pull of the Earth is about 1,400 times greater than the gravitational pull of the Sun. So essentially, the gravity of the Earth dictates the orbit of the Hubble. It's the gravitational pull of the Sun is almost negligible. Well, for the Webb telescope at its orbit at 1.5 million kilometers from the Earth, things have changed. Now we have basically plugged in all of these numbers, and we find out that for the Webb telescope, the gravitational force of the Earth is about only 3% of that of the Sun. So the gravitational force of the Sun dominates the orbit of the Webb, while gravitational force of the Earth dominates that of Hubble, or orbit of the Hubble. So I have rewritten these numbers basically in different ratios, but basically we can make the following statements. For Hubble at its orbit, the gravity of Earth dominates, with Sun contributing negligible 0.07% of gravitational force. Since Sun's gravity is such a negligible part of a total force, the Hubble trajectory can be considered to be a two-body problem between Hubble and the Earth. For the Webb at its orbit, the gravity of the Sun contributes 97% of the gravitational pull, and the Earth gravity contributes a non-negligible 3% of gravitational force. So Webb trajectory should then be considered to be a three-body problem. Three-body problem between the Sun, the Earth, and the Webb. So it looks like for Webb telescope, we got ourselves a three-body problem. These are the takeaways from this section. We say basically because Webb telescope senses infrared radiation, or otherwise known as a heat, for those who are not familiar with infrared, its sensors must be operating at very low temperature to avoid thermal noise from nearby sources of heat. To keep its sensors cold, Webb telescope operates at 1.5 million kilometers from the Earth and 150 million kilometers from the Sun. At that distance, the gravitational force from the Sun dominates gravitational force on Webb telescope, while the gravitational force from the Earth is still appreciable 3% of the total force. And because gravitational forces from the Sun and the Earth influence Webb's path, James Webb Telescope orbit is a three-body problem to which solutions were provided by Euler and Lagrange more than a quarter millennium ago. And now we go basically to Lagrange points. And this is these are basically the solutions to the three-body problem. I should point out these are solutions to the restricted three-body problem. By restricted three-body problem, we have to assume that there are two masses, such as the Sun and the Earth, which are way much greater than the mass of the object placed at the Lagrange point. As a matter of fact, we have to make a further restriction that the one mass of the two masses, large masses, is much bigger than the other. So the Sun is 300,000 times more massive than the Earth. And the Earth is billions times more massive than, let's say, Webb telescope. So we'll introduce you to the first three Lagrange points. There are 5 altogether. The L1, L2, and L3. They were discovered by Euler around 1760. And these 3 points lie on axis, which is between the center of the Sun and center of the Earth. The closest Lagrange point is L1. The L2 is which is between the Earth and the Sun and the Earth. L2 is next closest one, which is really further away from the Sun, but close to the Earth. And L2 is, actually, the closest one is L2. The L2 is closer to the Earth than L1 by about 10,000 kilometers. And I have a disclaimer here, which you can read, that basically we are using here mean values for the planetary distances. So these distances are not really truly accurate to the next kilometer, but they have a meaning in comparison of the two values that differ only by a few kilometers or a few tens of kilometers. So L2 is closer to the Sun, closer to the Earth than L1 only by 10,000 kilometers. The distance between L2 and the Earth is 1.5 million kilometers. The L3 is on the other side of the Sun. It is essentially at very similar distance from the Sun than the Earth is. The difference between the L3 orbit and L2 orbit is only 263 kilometers. So we can make a statement that all these Lagrange points are in orbit which is very similar to the Earth orbit. Now we go to the L4 and L5. Those were discovered by Lagrange about 10 years after Euler discovered L1, 2, and 3. And I should point out that there is a connection between Euler and Lagrange, because Lagrange was Euler's graduate student in University of Basel in Switzerland when Euler was in Switzerland. Euler spent a lot of time in Russia, but this was the time where he spent in Switzerland. So I am pretty sure that the Lagrange was familiar with Euler's work on L1 and 2 and 3, and this might be a case of a graduate student trying to outdo his professor. But anyway, the points L4 and L5 lie at the vertices of of equilateral triangles whose base joins Sun and the Earth. For those who might have forgotten, equilateral triangle is a triangle which has 3 identical sides. And therefore, the angle between these sides is 60 degrees. Because these are 3 identical sides, the L4 and L5 orbit is distance from the Sun is again the same as that of the Earth from the Sun. So, as a summary for all of them, we can say there are certain similarities between Lagrange points. The orbital periods of all Earth Lagrange points are exactly the same as Earth orbital point period. Of course, that's obvious because we are trying to find points which are stationary with respect to the Earth. So they have to be in exactly the same period orbital. And we can say that all Lagrange points are positioned approximately at the same distance from the Sun, give or take 1%. We'll do some math now. We will calculate the position of the Lagrange point L2 and later calculate the position of Lagrange point L4 and 5. And for this particular, for the L2, the discussion that I'm going to present is based on a YouTube video by Abhishek Shashan entitled Finding Lagrange Point 2, where James Webb Telescope will be deployed. And Walt has provided you all of the YouTube addresses when he announced this talk. So just to frame the problem, we have on the left a picture of the Sun with mass capital M, the Earth with mass small m, and picture of an object at Lagrange point such as Webb, whose mass is very small m prime. We will assume that the Sun is much greater than the Earth. We don't have to assume it, we know it's the case. We also assume that the Webb satellite is much smaller than the Earth, and that's obvious. This simplification, and it's restricted by the problem, allows us to use circular orbits around the center of the Earth, around the center of the Sun for both the Earth and the Sun, for both the Earth and the Webb satellite. So now, in order for let's first consider the Earth. In order for the Earth to orbit a circle around the Sun, we have to say that centrifugal force, or centrifugal force, is equals to the force of gravitation. For the purists who would say there is no such thing as centrifugal force or centripetal force, I would say that if we have a circular orbit, the concept of centrifugal force makes sense, because that force is more or less constant in a circular orbit. And from either high school physics or freshman physics, we know the centrifugal force is, the formula for centrifugal force is mass times velocity squared divided by distance to the center of the orbit. So for the Earth, centrifugal force is a mass of the Earth, little m, times v1 squared, that's the velocity of the Earth, divided by the distance between the center of the mass of the Earth and center mass of the Sun. Since we have to have equivalence of forces, centrifugal forces and gravitational forces, we can use Newton's formula to compute what is the gravitational pull of the Earth. And that's basically Newton's formula, where capital M is the mass of the Sun, small m is the mass of the Earth, and R1 is distance between the centers of the Earth, of the Sun and the Earth squared. This allows us to solve what the V1 is in terms of known constants. We know what the mass of the Sun is, and we know what the distance between Sun and the Earth is. Now we will, in order to keep this the distance, excuse me. Now, in order to keep the distance between the the Earth and the Lagrange point constant, which is what we really want, we have to assume that the angular velocity, which is defined by this relationship, it's basically a rotation. It's how quickly the object rotates. We have to assume that the angular velocity of the satellite at the Lagrange point and the Earth has to be constant. Now we know the definition of angular velocity is omega is equal to speed divided by the distance between Earth and the Sun, and this is for the Earth. And the angular velocity of the object at the Lagrange point is equal also to the velocity of the object at the Lagrange point divided by the sum of the distances between the center of the Sun to the Earth and from the center of the Earth to the Lagrange point. So this is a formula for the angular velocity of the object in Lagrange point. And as I said, they have to be equal in order for Lagrange point to be stationary with respect to the Earth. So now we can compute, basically express that in terms of velocities. And we get this equation for the velocity of the object at the Lagrange point in terms of velocity of the Earth and the distances between the distance between the Earth and the Lagrange point, and also distance between the Earth and the Sun. We already computed what the V1 is, which is the speed of the velocity of the Earth. So we can plug it in here, and we're getting this equation here for what a V2 is, which is the velocity of the object at the Lagrange point. Now, we can make the same argument that at Lagrange point, the centrifugal force of the object has to be equal to the gravitational force. Centrifugal force, as I mentioned, it's mv squared over distance to the center of the object. So here we have basically centrifugal force, it's m of the satellite at Lagrange point times velocity of that object at Lagrange point divided by sum of these distances, sum of distance between the center of the Sun to the Earth and from the center of the Earth to the Lagrange point. The gravitational force here, we have basically a gravitational pull from both the Sun, which is this one, and the Earth, which is this one. And now we go through some algebra since we already calculated what the V2 is. Substitute here, and we get the equation starts looking like a polynomial. And if you look at this equation, pretty much everything here is known except D. G is a gravitational constant. The capital M is the mass of the Sun. Little m prime is a mass of Webb telescope, but we don't need to worry about it because it's on both sides of the equation. We know the R1, it's a distance between the Earth and the Sun. What we don't know is D, and this is what we're going to try to calculate. So we have rewritten the equation here. We can simplify further by getting rid of the capital G's and M's, and we get this polynomial, which we can simplify further by multiplying out the denominators, and this is basically a polynomial, which is an expression to calculate the distance between the center of the Earth to the Lagrange point in terms of known quantities such as mass of the Sun, mass of the Earth, and distance between the Earth and the Sun. We are trying to solve here for D. If you look at it, this is essentially a 5th degree polynomial. Not something that you would really want to solve analytically, and definitely not something I would want to present in this talk because it would take time. So we'll solve it numerically. We know all of these constants are. We know that the mass of the Sun is 2 times 10 to the 30th kilograms. Mass of the Earth is about 6 times 10 to the 24th kilograms, and the distance between the Earth and the Sun is about 150 million kilometers. To solve this, I used Mathematica, because it's a program that's basically set up very nicely to solve polynomials. And it takes very little programming to do that. And this is essentially a mathematical solution for this problem. It takes only 5 statements in a program to solve it, 3 of which are declaratory statements where the value of the constants is. So we basically define the value of mass of the sun, value of mass of the earth, and distance between the sun and the earth. Then for Mathematica, we input this equation from a previous view graph. And this is basically the input equation in algebraic form. Mathematica substitutes numerical values of constants in equation, which basically we come up with this equation where all of the constants are now substituted by their numerical value. We tell Mathematica to solve this equation to 0, to set this equation to 0 and solve the above equation. And less than a second later, Mathematica comes with 5 roots, 4 of which are complex, but the 5th one is real. And voila, it is 1.5 times 10 to the 6 kilometers, which is where L2 is. And just to verify it, this is a web page from Goddard Space Flight Center. Says James Webb Telescope will not be in orbit around the Earth like Hubble Space Telescope. It will actually orbit the sun 1.5 million kilometers away from the Earth. It's what's called the second Lagrange point, or L2. So our calculation, although he made all of these simplifications, gave us value who just, which is the right value. So much for the L1, 2, and 3. Now let's discuss L4 and L5. And this particular discussion is based on 2 excellent articles. One is the Lagrange point by Neil Cornish, dated 1998. Neil Cornish was in NASA. And another article is by Dennis Westra from about 20 years later. And I believe Dennis Westra was at that time in University of Vienna. So first we'll frame the problem. And since now we are dealing with 2-dimensional problem, because the Lagrange point we are looking for is not on the axis between the Earth and the sun. We are going to place a sun with mass m1, Earth with mass m2, and a Lagrange point, an object at Lagrange point with mass lowercase m. Now, the distance is, it is convenient for this particular calculation to use a coordinates which are at the center of mass of both the m1 and m2. So we will call that point C. And essentially this, because it is the center of mass, we can say that by the definition of the center of mass, we can say that m1 times r1, which is m1, which is mass of the Earth times the distance from the center of the gravity for both objects to the center of gravity of sun, that's r1, equals m2 r2, where r2 is the distance between the center of gravity both to the center of gravity of the Earth, and r2 is the distances between the 2 centers. Now notice that I'm using here a vector notation. In the scalar notation, we would say m1 r1 equals m2 r2. However, here I have vectors which are pointing in opposite directions. So this is why I'm using m1 r1 plus m2 r2 equals 0. Now this is a rotating reference or co-rotating reference frame in which Earth and Sun are separated by constant distance, which is r1 plus r2. This is again in scalar form, it is r1 plus 2, in vector form will be r1 minus r2. And the frame is rotating about the Earth system center of mass with angular velocity omega, which is given by Kepler's law. And that law says that the center of mass of this system will operate at omega, which is the square root of gravitational force times sum of the two masses divided by cube of a distance between R1 and R2. I should point out that the vertical brackets here imply a distance, or the length of a vector. So we are taking vectors, so you're basically making them a scalar quantity, and that's what the vertical brackets do. So now we can compute what is the gravitational force on this object from both the M1, which is the Sun, and M2, which is the Earth. And this is essentially using Newton's formula with one caveat. We are now using a vector form of this equation. So we have to introduce what I would call a unity vector, whose value is unity, but which contains information about the direction of the vector. So because force is a vector, we have to make this equation in vector form. So definition of a unity vector for this quantity r minus r1 equals to r minus r1 in vector form divided by a scalar value, which is r minus r1 in the brackets. Because of this, the square terms in denominator of the Newton's formula now become cubic terms in a scalar form. Similar thing for the Earth. In vector form, we have a cubic version, cube of the distance between the Earth and the satellite. We again look at the centrifugal force on the satellite at the Lagrange point, and again we assume it's a circular orbit, which is actually, for this computation, is quite a good approximation. So it's again mv squared over r. It is more convenient now to introduce the angular velocity vector, which is omega, which is equal to v over r, where v is a vector. So we can say the centrifugal force is equal to m omega squared times r. Again, r is a vector here. Now we already know that Kepler gave us equation for what omega is, which is the angular velocity. So we can substitute that omega into the equation for the centrifugal force. And after we multiply it out, we get this equation, which actually, if you look at it, it starts looking kind of similar in nature to the equation given by Newton's formula for the gravitational attraction between the objects. So we have now force of gravity, which is given by this formula, this Newton's formula for both the Sun and the Earth. And we have centrifugal force, which is this formula, given using Kepler's equation. So either at L4 or L5, the centrifugal gravitational force has to be equal to centrifugal force. We can write this equation. Basically, this is the equation for the gravitational force. This is from the Sun, this is from the Earth. And this is equation for centrifugal force using Kepler's equation. So we can simplify this equation by getting rid of the redundant terms. And we get this interesting equation. Now, at first blush, it's actually it is a complex equation. If we did this using traditional methods, we would find the most common denominator and then multiply out the denominators. And I think we would wind up with the 7th order polynomial in R. I mean, R1 or R2, or I mean, in a distance. But we also know that since we are at this particular point we calculate of the origin, which is the center of mass origin, that this equation forms. Now, wouldn't it be nice if we got rid of these pesky denominators and see if, given this condition, whether the numerator satisfies this equality? And this is what we will do. We will assume that the distance between the r minus r2 equals to r minus r1 equals r1 minus r2. So we'll assume that they're equal to each other. That allows us to get rid of these denominators from the equation. And we'll check whether the numerator of this equation actually holds given this particular condition. So we do this. Now it's a much simpler equation. Basically, this is the equation for the denominator after we have gotten rid of denominators. This is a center of mass equation. We arrange terms very simple, and we get equality. Voila! So we have found a solution to the 7th order polynomial by making a guess, and the guess is right. It basically says that these denominators have to be exactly the same to each other. Now, what does it mean? Well, r minus r2 is distance between the center of the Earth, Sun to the center of the Earth. R minus R1 is equal to the distance between the center of the Sun to the Lagrange point. And R minus 2 is equal to the distance between the center of the Earth and Lagrange point. So what it tells us is this is an equilateral triangle. These distances are all identical. So you can make a statement basically that L4 and L5 are points in the plane of rotation that makes the three masses lie on vertices of an equilateral triangle. Again, an equilateral triangle is one has three identical sides, where the distances between the Sun and the Earth are the same as distances to L4, L5, or L5 from the Earth and the Sun. And if you look at the web and you Google Lagrange point, it is more likely than not you'll get to see this kind of a figure for Lagrange points. This is L4 and this is L5, and this is our equilateral triangle. Since the distance between Sun and the Earth is the same as the distance between center of the Sun and the L4, the L4 and L5 lie on the identical orbit to the Earth. So here are the takeaways from this discussion. The L1, 2, and 3 computation is a one-dimensional problem that yields a fifth degree polynomial that can be solved analytically if you have a patience and a fortitude. But otherwise, the easier method nowadays, because we have computers, is to solve this polynomial numerically to compute distances from Earth of these Lagrange points. L4 and L5 computation problems, despite of their apparent complexity, can be solved analytically using Kepler's equation without having to solve high-degree polynomial. Okay, so now we have defined the 5 Lagrange points. The question is how stable they are. And let me define what I mean by stability. Let's say I put an object at Lagrange point, any one of them, and that object gets perturbed, its path gets perturbed at the Lagrange point. The question is it going to come back to the Lagrange point, in which case we consider the Lagrange point to be stable, or is it going to go fly away from the Lagrange point, in which case Lagrange point would be unstable. So stability is kind of important, because if you place a satellite at Lagrange point, you want to know whether you have to do anything to keep it there, in that particular orbit. Now we will try to define what is equilibrium of gravitational forces in terms of gravitational potential. So it's a little bit of simple mechanics. We let U to be the gravitational potential of an object in space act by net gravitational force F. U is really a work that's needed to move an object from point R1 to R2 along the gravitational force. So we basically push the object against the gravitational force. We do work, which is defined as U, and therefore U is defined as an integral of force in the times distance in direction parallel to the force. You can think of, if you're climbing up the hill, for example, you are gaining gravitational potential because you're doing work coming up higher. So you are doing work to get yourself from lower point to the higher point. This is basically what the U is. It's work that is required to move you to a different place in the gravitational plane. Since U is an integral of force times distance, we know that force is essentially derivative of this, and this is a three-dimensional derivative with del, or nowadays also called nabla, which is basically defined by this formula. Now, U is a scalar, F is a force, and this particular operator, the scalar or the del nabla or del operator, has the information about direction in direction x, y, and z. So this operator looks at derivative in different directions and makes a vector out of it. Now we know that the equilibrium, the gravitational force acting on the object has to be zero. This is the definition, basically how we define Lagrange point. Since force is a derivative of a potential, when force is zero, or the derivative of potential is zero, the gravitational potential has to be either minimum or maximum value. This is essentially a first-year high school or first-year calculus. Here are some examples of equilibria in 2 dimensions, and I'll show you later what they look like in 3 dimensions. But let's assume we have a gravitational potential which looks like this. It could be parabola, it could be anything, but has basically this kind of shape. And we place object in this gravitational equilibrium. If this particular object moves to either left or right, there will be a force acting on this object to come to the lowest point. So at minimum, this is a minimum, this gravitational potential, we have a stable equilibrium. If we now look at the maximum of a gravitational point, which is as illustrated in this kind of example, if we place an object at the maximum gravitational potential, and that object gets displaced by any kind of perturbation, it's not going to come back to its maximum point. It's going to fly down the gravitational potential curve, and unless you use extra energy, it's not going to come back to its equilibrium. We can have also a neutral equilibrium, which is essentially a straight line. In this particular equilibrium, the object can move left or right, and depending whether this gravitational equilibrium eventually curves up or down, you can have a stable or unstable equilibrium. There are degrees of stability of unstable equilibrium points. If I have a curve which is sharply defined, I have essentially, and I place the object to it, it's not going to stay here long. It's going to fall down and fall down very quickly. So we can say that at this particular unstable equilibrium, this object has a fairly short lifetime of staying in this on the top. If you have a gentle hill, a gentle curve, and you place an object here, it is going to take a while for this object to come down and roll down the gravitational potential. We call this metastable, and this particular object will have a longer lifetime. Now let's look at these equilibria 3 dimensions. Well, we have the valleys, which is basically stable equilibrium. That's equivalent to that parabola-like shape used in 2 dimensions. We have hills which are unstable. If you place an object here, it's going to come down. It's not going to come back. But we have a new kind of equilibrium, which is unique to 3 dimensions, which does not exist in 2 dimensions. We call it saddle point. It is a equilibrium where it's stable in one direction, in this direction, for example, which will be the x direction, and it's unstable in this direction, which is z direction, because in this direction we are at the minimum of a potential of gravitational potential. In this direction we are at the maximum of the gravitational potential. And of course we have again mutual equilibrium, which is horizontal plane. It's similar to the line in 2 dimensions. So now what we will do is build gravitational potential for the Earth, for the Sun-Earth system. So we have a Sun here, we have Earth here, of course not to scale, and this grid represents basically gravitational potential. So the gravitational potential for the Sun looks like that. It's a valley, and it makes sense because if I place an object close to the Sun, it's going to get attracted to the center of the Sun. So it's going to go down this potential equilibrium, and it will take energy to get it out if I want to get it out. Similar thing for the Earth, smaller but similar in shape. And if I add these two, you can see that now I am getting a region in the gravitational field where the derivative of the field is equal to 0. I'm basically here at the maximum, excuse me, at the maximum potential, gravitational potential of the field. Well, we will take a look at it, excuse me, at lower magnification. And that's our friend L1. And if you can look at it, it is actually a saddle point. It is unstable on the axis between the Sun and the Earth, this direction, because it's a maximum in this direction, and it's a minimum perpendicular to this axis, which is in this direction. So this is the saddle point. It turns out L2 is another saddle point, perhaps not as sharply defined as L1, and L3 is yet another saddle point. So we have 3 saddle points, L1 and L3. Now let's ask the question, what does L4 and L5 looks like? Well, L4 is not at the saddle point. It is on the top of a hill, gravitational hill. There's no minimum involved here. It's only maximum involved. And so is L5. And here are our familiar equilateral triangles between L4 and 5, L4, Earth and the Sun. So from a gravitational point of view, we can make the following statements. L1, 2, and 3 are saddle points with gentle slopes. L4 and L5 are hills also with gentle slopes. But from gravitational point of view, we can make a statement that all Lagrange points, L1, 2, 3, 4, and 5, can be considered to be unstable or metastable. But, L4 and 5 are considered to be stable despite their gravitational potential, and that makes them meta or unstable. Why is that? Well, there's a second order effect, which is known as Coriolis force. And it basically says as the body moves away from the exact Lagrange point of view position, Coriolis acceleration, which depends on the velocity of orbiting object and cannot be modeled as a contour map, curves the trajectory into a path around rather than away from that point. And I will have this video by Scott Manley, which will illustrate basically the point. And then after that video, we will go through the math of the Coriolis force.
Many of you will have heard that L4 and L5 are stable. But if you look at this, that doesn't look stable, right? Those things, if they're pushed slightly away from those hilltops, they'll tend to roll downhill and
Okay, what I want to show, what Scott is doing is, this is Earth-Moon system, rather Earth-Sun system, but it does have Lagrange points, basically it's a three-body system. What Scott did is he placed two objects at Lagrange point, will be L4 and L5. This is one Lagrange point, this is the other Lagrange point. Here's the moon, which is his orbit. And the orbit of the moon, he placed also a bunch of objects at random points of the orbit. What he's going to do now is to run a simulation, letting these things orbit, and see what falls out of this orbit and what stays in this orbit.
away from the Lagrange point. And look, here's a really simple demo where I've got the moon and the Earth and some objects in the same orbit as the moon, and we run time forwards, and very quickly a lot of the objects get kicked off into different orbits.
Okay. So now if we stop it again, we can see that most of the objects have fallen out of the moon's orbit. What stays in moon's orbit is moon, trailing Lagrange point, and Lagrange point. Everything else has basically left the orbit. That's what makes Lagrange points Lagrange points. Essentially, the force, the sum of the forces of Lagrange points is zero. There is no, so there's nothing to throw them off the orbit.
Some fall down, some go up, but the objects in L4 and L5 remain in the same places. And the reason they can remain here is because of the Coriolis force. You see, all these potential surfaces we've been drawing are assuming a rotating environment with a fixed object. But as soon as an object starts moving in a rotating environment, it experiences the Coriolis force. So this force is always going to be at 90 degrees to the direction of motion. And if you've got a force at 90 degrees to the direction of motion, it forces you to move in circles. And so that's why L4 and L5 can be stable. But wait, I hear you say, why doesn't the Coriolis force stabilize the other Lagrange points? And the answer is the Coriolis force isn't the only thing acting on it. It's also got the forces from this, rolling around on these curved surfaces. And if it starts at L1 through 3, then it's on a saddle point. If it rolls down away from it, it comes sideways and it gets pushed back up, it's going to find that it has to go up higher, which would mean it would need to get energy from somewhere. So the saddle points don't really support this kind of rotation. Now, if you start up on the edge of the ridge, then there are ways to move around this, but they're not stable. But the other thing is, the Coriolis force is only sufficient if the curvature near the point is sufficiently low, if things don't go downhill too fast. The shape of this potential surface depends upon the mass ratio between the primary and the secondary body. And as the secondary body gets larger, the peaks at L4 and L5 become sharper, and that makes them less and less forgiving to the Coriolis force. So it turns out that if the mass of the secondary body is more than about 1/25th of the mass of the primary, then L4 and L5 are no longer stable. Any of you will have heard.
Okay, so here is a summary of the concepts in the video. The L4 and L5 are stable due to Coriolis force if mass ratio between the two objects is greater than 25. L1 through 3 are not stable because the saddle point potential creates a potential barrier to a circular trajectory created by the Coriolis force. So what is this Coriolis force? Well, we are familiar with the Coriolis force because we see hurricanes. It essentially, the Earth is a rotating body, and if there's any motion of the air which is along the surface, the Coriolis force will make it curve, and actually it will make it go in the circular dimension. Now this is better, we can explain mathematically. Coriolis force is an inertia of fictitious force that acts on objects in motion within a frame of reference that rotates with respect to the inertial frame. You can see here, for example, we have a stationary reference frame where the object travels in a straight line, but in the rotating reference frame, the object's path is curved. The mathematical formulation of Coriolis force Fc, which is a vector, because it's a force. It's equal minus 2m, where m is the mass of the object that is in a rotating reference frame, times cross product of the angular velocity times linear velocity, or tangential velocity. Since this is a cross product, it's a vector product, direction of this Coriolis force is perpendicular to both omega and v. So now let's assume this. We'll try to explain how this happens in another diagram. Let's assume where we have a mass and place that in the orbit of a Lagrange point, either L4 or L5. If now we perturb its path temporarily by a force, we'll call it Fp, it will accelerate this and gain some velocity, which has a component which is perpendicular to the angular velocity vector omega, which is perpendicular to the rotation. So now we have two vectors which are perpendicular to each other, which result in a Coriolis force which is perpendicular to both, and this is the Coriolis force. So now we have an object which is moving towards, let's say, towards the center, but now has a Coriolis force which makes its path curve. Another way to look at it is perhaps with another view. Here is our mass. Here is our velocity component, which is perpendicular to the omega vector, which will be going in or out of the view graph. Here's our Coriolis force, and here is our curved path. The property of Coriolis force is that no matter where you are on the rotating reference frame, the Coriolis force always bends in the same direction, which for me is a prescription for a circular motion. And what we have now is a video which will explain, which will give you basically an idea what happens to an object at position, for example, in this case, it's at L4, which will be perturbed from its path, and how Coriolis force makes it basically come back to its path. So here's the video. And you can see the object is circling the L4 and eventually comes back to the L4. So the takeaways from this discussion, from the discussion of stability of these points, is that from gravitational point of view, all Lagrange points are unstable or metastable, with L1 through 3 being potential saddle points with gentle slopes, and L4 and 5 potential fields with gentle slopes as well. The L4 and 5 are, however, stable because Coriolis force that acts perpendicular to the motion of a mass that is, of course, for a Lagrange point, makes it move in circular motion. I should point out that the Coriolis force around these Lagrange points can also give an object what's known as a phantom trajectory. There are trajectories called horseshoe trajectories, they're called tadpole trajectories. This is another subject, but these particular orbits can be quite complicated and it can take quite a bit of time to complete for the object to come back to its Lagrange point. So what I have shown in the video is a very nice case, very simple case. In reality, these things can get much more complicated, and the time for the object to come back to the Lagrange point can be very long. Okay, so we are done now with the Lagrange points. We will now discuss the Webb telescope, orbit, and its architecture requirements. Well, here are the construction requirements for the Webb telescope. It has infrared optics, which has to be facing away from any source of infrared radiation, such as the sun, the earth, and the moon, or anything else that will radiate heat. The power source, which is a solar panel for the Webb telescope, has to face a source of light, such as the sun. So we have to have a cold side, which houses the infrared optics, and the solar panels, which have to face a source of radiation, which is warm side or hot side. they really have to face the opposite side of a telescope. To minimize the heat transfer between the warm side to the cold side, one has to install a heat shield that dissipates heat through radiation. And the course adjustment thrusters, which are placed, which adjust the course, the position of the telescope, can be only put on a hot side, since they generate heat and condensable gases. The last thing you want to do is have a cold side, which I will show you. It's about 45 degrees Kelvin. It's very cold, and have the exhaust gas condense on that part of the satellite, particularly condense on the infrared optics. That would basically ruin the entire experiment. The electronics controlling the spacecraft and the infrared lenses and the communication circuits need to consume minimal power to keep the interior of the cold side from warming up. Now, this is a sort of a diagram of what the Webb telescope looks like. We have a cold side, which is operated at minus 233 degrees centigrade, which contains the mirrors, the detectors, and any science instruments that basically analyze the radiation. This is a cold side. The warm side on the other side faces the sun. It's at 85 degrees centigrade, so the difference between the cold side and the warm side is 300 degrees centigrade. For comparison, the difference between boiling water and freezing is 100 degrees centigrade. So this is 3 times as much as temperature required that you can bring water from ice to vapor. Now, the hot side has a solar panel for electricity, has communications antenna, has a computer, and has a steering and reaction wheels and jets to basically maintain the position of the telescope, so it's facing the sun to get the most light. We will make now a case for the Lagrange point L2, as opposed to other Lagrange points, for the Webb telescope. This is where the telescope has been NASA has chosen L2 as the place to put the Webb telescope. So at L2, the Earth, Sun, and Moon will be all in the same direction. This is the Sun, this is the Earth, this is the Moon. So this allows a shielding to face in one direction, a shield from all 3 at the same time. It allows more flexibility in aiming the scope for a similar reason, because once you have a shield here, the scope can basically face any direction in this part, in this heavy semicircle here. Now, the reason why NASA did not choose L1 is because at Earth and Sun are in the opposite direction, so there's no possibility for the warm and hot side of the telescope. At L4 and L5, the Sun and the Earth are not lined up. You would need really 2 separate shields, one for the Sun and one for the Earth, facing a different direction. It would make a much more complicated structure. But there are some other reasons why L2 was chosen over L5, and that has to do with the transmission power. L2, although it's not shown in the picture because it's not scale, is 100 times closer to the Earth than L4 and L5. So this has following implications on communications. First, the transit time. The transit time of information between the Earth and the Webb telescope is now, at L2, is about 5 seconds. For L4 or L5, it would have been 100 times longer. It would be about over 8 minutes. The transit time of 8 minutes really makes it impossible for effective communications with the Webb telescope, particularly when you have to have interactive communications where human intervention is needed. A second reason why L2 is better than L4 and L5 is that at L2 one can use a 5-watt Ka band transmitter to transmit information back to Earth. At L4 and L5, because it is 100 times further, that 5-watt transmitter will have to turn it into 50 kilowatt transmitter. There are real problems with 50 kilowatt transmitter. First, the operation of Webb telescope is extremely sensitive to ambient heat, and 50 kilowatt transmitter would be the last thing you want to have around a satellite that you're trying to keep cold. So the 50 kilowatt transmitter would warm the telescope to the unacceptable levels and would drastically decrease Webb telescope's ability to sense infrared radiation. A second reason is that solar panels of Webb telescope can provide 2 kilowatts of power in the current version. They are not adequate for the 50 kilowatt transmitter. If one really wanted to brute force it and make a 50 kilowatt solar panels, they'll be so big that you'll probably not be able to sort of neatly fold the whole satellite and place it on the top of the Ariane rocket, which is what has been done to fly it basically into space. Now, the L2 is not stable. Neither are the other points. But there's a lot of experience in operating similar aircraft at L2 for many years. And this is the list of some of the satellites that have been flying at L2. And I don't need to go through every one of them, but I just want to point out that the longest that the satellite has stayed at L2 was about 9 years, from October 2001 to October 2010. There was Wilkinson microwave anisotropy probe. And this is because you have to have a fuel to correct because it's not a stable point, you have to have a fuel to periodically correct the trajectory of the satellite so it does not fly into space, into oblivion. The other reason why L2 is desirable, it actually has to do with the fact that it is unstable, and that in this case is actually desirable because unstable point does not collect objects like L4 and L5 do. So any object that finds itself around L2 will fly off. Any object at L4 and 5 will stay in the orbit. So L2, the Webb telescope is object to a big chunk of sky, essentially, 180 degrees, without the Earth and Moon and thousands of space readiness objects called SROs obstructing that field of view. Well, all of this does not come without a price. We know that L2 is a saddle point, we already established that, which is unstable along the Sun-Earth axis, but stable in the other directions. So most of the station keeping effort goes into keeping the desired distance from the sun. It's actually quite complicated because L2 has thrusters only placed on one side of the telescope. It's on the hot side of the telescope, so it can only push the telescope. There are no thrusters which can pull it back. So if those thrusters push the satellite beyond the L2 here, beyond the saddle point, there's no way for the satellite to come back. There are no thrusters which will bring it back. So one has to be very careful with the operation of the satellite at L2. The other problem with L2 is that a Webb telescope at L2, the Webb telescope will be in Earth shadow where solar panels will not work. because the sun will be mostly eclipsed by the Earth. It will be basically in a line between the sun and the Earth will be positioned in line between the sun and the Webb telescope. So one has to, in order to circumvent that problem, has to use something called halo orbit around it, which is most economical way to keep in position where it can receive maximum power from the sun. And we'll illustrate it in the following view graph. The periodic adjustments of the Webb telescope, therefore, will be needed. And the problem is that the lifetime of this telescope is determined by the fuel capacity of the spacecraft. The Webb telescope was designed to last about 10 years because of the fuel budget. Now, this is a halo orbit for Webb telescope. It is actually not to scale, but essentially it shows that if you operate around L2, you can actually get sunlight from the sun. This is, as I said, it's not to scale. I have one picture here which is to scale. This is the Earth. This is the Moon. Lunar orbit is about 477,000 miles. This is the L2 orbit of the Webb telescope. It's not circular, it's sort of elliptical. The major distance from the top to bottom of this ellipse is about 1 million miles. So I'm going to finish this particular presentation with the video, which is entitled "How Webb Orbits Nothing" by Christian Reddy. And I should point out that Christian Reddy was in the last talk by John Tomaszewski. Christian Reddy talked about the Webb telescope and mostly its characteristics. Here, he will give a talk about its orbit.
After a 1.5 million kilometer journey, the James Webb Space Telescope has arrived at the Sun-Earth L2 point. It did this by executing its final mid-course correction burn called MCC2. It lasted just 297 seconds, or a little less than 5 minutes, and it only changed Webb's speed by about 1.5 meters per second. That's a brisk walking pace. It may not seem like much, but it was enough to place Webb into an orbit around L2. In fact, it placed it into a very large orbit, one that's more than twice as large as the Moon's orbit around Earth. It'll take Webb about 6 months to complete a single orbit around L2, and this first go-around is jam-packed with mirror alignments, phasing, instrument calibrations, moving target tracking tests, verifications, station-keeping maneuvers, and finally, the first science observations. But what exactly is so special about L2? I mean, it's just a point in space, and it's an empty point in space at that, so how can Webb orbit something that isn't there? Well, it is true that L2 is empty, but orbiting empty points in space is actually very common. And that's because whenever there are two massive bodies that are orbiting each other, they both orbit a common center of mass, or barycenter. If the objects are massive enough, the center of mass lies somewhere in between. We only say that the Moon orbits Earth because its center of mass is located inside Earth. But Pluto and Charon have similar masses, so their barycenter is somewhere in the space between them. So the fact that something can orbit an empty point in space really isn't all that unusual. But at the same time, that's a two-body system. It doesn't explain how Webb can orbit a point that's outside of another two-body system. Well, the good news is that we can break this problem down and understand just what the L2 point is and how Webb can orbit around it. In fact, there are many spacecraft that have orbited L2, such as NASA's WMAP satellite and ESA's Planck and Herschel telescopes, and Russia's Spectre RG and ESA's Gaia spacecraft are both orbiting there today. L2 is one of the 5 Lagrangian points between the Sun and Earth. Actually, these 5 points exist around any two-body system. So there are Lagrangian points for the Earth-Moon system, a set of points for the Sun-Jupiter system, and so on. Now, if a third object is placed at any of these points, the gravitational forces of the two large bodies combine in such a way that holds the third object stable with respect to the others. The practical upshot is that as the system orbits, the third body tags along. And that's why the Sun-Earth L1 point is a great place to position sun-facing missions like the Solar Heliospheric Observatory and Earth-facing missions like DISCOVER. Likewise, L2 is the place to put astrophysics missions like Gaia and Webb. At both locations, spacecraft maintain a constant line-of-sight communication with Earth even as Earth orbits the Sun. But L2 is particularly important for Webb because it can block the heat of the Sun, Earth, and Moon with a single sun shield. That's a perfect place for infrared astronomy. But there are some important caveats. For one thing, the third object has to have a mass that's really small relative to the larger bodies. Now, obviously, that's not a problem. Webb's mass is negligible compared to Earth, let alone the Sun. But the other caveat is that the Lagrangian points are at best described as metastable, especially the first 3 points. To understand what I mean, imagine a saddle that's perfectly smooth and frictionless. Now imagine trying to balance a marble in the very center of the saddle. It's theoretically possible, but as a practical matter, it's extremely hard to do. The L2 point is a lot like this. An object moving perpendicular to the Sun-Earth line falls toward the center, but then it either falls toward or away from Earth. Now, if Webb falls away from Earth, it's really in trouble because the only way to bring it back would be to turn it around and thrust back. But that would cause the telescope to suddenly warm up, all of the structures would expand, glues and adhesives would melt, and the mission would be over. And that's bad. Webb has thrusters only on the warm, sun-facing side of the observatory. And that's because hot thrusters would contaminate the cold telescope side with heat or with rocket exhaust that would otherwise condense on the optics. And that would also be bad. A safer approach is to place Webb almost, but not quite at L2. And that way, when it falls back toward Earth, a tiny thruster burn pushes it back almost, but not quite, back to L2. And this means Webb never runs the risk of actually falling beyond L2 where it cannot be recovered. And that's why the Ariane 5 launch was intentionally designed to slightly undershoot and let the spacecraft do a series of mid-course correction burns. The first two, MCC-1A and MCC-1B, were executed on the way out to L2. However, arriving even just shy of L2 leaves us with another problem. At that distance, the Sun is in a permanent annular eclipse by Earth. Webb is solar-powered. Now, it could use nuclear power, but that's expensive and hard to do. Another complication is that Coriolis forces would cause Webb to librate around L2. In other words, Webb would find itself in a tiny orbit around L2 that would need even more thruster burns to manage. Oh, and the Moon's gravity on Webb is also still a thing, and it's constantly varying as it orbits Earth. It turns out that these real-world complications can be addressed by simply taking up a large orbit around L2. But how is it possible to orbit something that isn't there? I mean, L2 is still an empty point in space. Well, to help us understand better, let's look at the problem by considering some of the forces acting on Webb. If Webb were actually at L2, it would be feeling gravitational forces from the Sun and from Earth. So let's draw them separately so that we can keep track of them. Now, Webb is orbiting the Sun at the same time, so we can also imagine a centrifugal force pulling Webb in the opposite direction. Now, the great thing about L2 is that at this distance, the centrifugal force is exactly balanced by the gravity of the Earth and Sun. Now, you may have heard that there's no such thing as a centrifugal force, and that is correct. But we are talking about a rotating non-inertial frame here, so centrifugal forces are still a useful way of summarizing all of the real effects that are going on. Oh, and we're not going to worry about the gravitational effects of the Moon or even the fact that the Sun and the Earth are not point sources. We're just going to keep everything simple for the time being. Now let's move Webb up some distance away from L2. Now, the gravitational force from the Sun changes a tiny amount, but not very much because it's over 150 million kilometers away. But Earth is just 1% of that distance, so its gravity changes considerably. Because Webb is now farther away from Earth, its gravitational pull gets weaker. It's also no longer parallel with the Sun's direction either. So let's break it up into its x and y components. Now we can really see the problem. The centrifugal force is in the x direction of our diagram, but it's actually greater than the gravitational forces from the Sun and Earth. That means Webb is going to drift both down and farther away from L2. So we need to fix this drift in both the x and y directions. First, we bring Webb a little closer to Earth so that it's now hovering above a new point that we'll just call L2 prime. Earth's gravity gets stronger, and its x component helps to balance the centrifugal force once again. But the y component has gotten stronger as well, so Webb wants to move downward. But the closer it gets to the Sun-Earth line, the stronger Earth's gravity gets and the more it moves toward Earth. We can't let that happen either, because then the heat load would become too strong for the sun shield to handle. However, we can counteract this downward force by giving Webb a sideways push into the screen. This sets up a new centrifugal force that balances the downward force of Earth's gravity. When combined with the sideways motion, Webb takes up a new circular halo orbit around L2 prime. And that means there doesn't have to be a physical mass at L2 prime in order to attract Webb. Rather, Webb is simply being pulled by the y component of Earth's gravitational force. Now, this is an oversimplified discussion of Webb's orbit around L2. We deliberately ignored real-world complications in order to understand how Webb can orbit something that isn't there. But getting into Webb's actual orbit required taking all of these real-world complications into account. So, to make things easier, Webb wasn't actually launched to L2. Instead, it was launched to a point along the side of L2. As it was starting to fall away, Webb executed its MCC-2 burn to settle into its orbit. Since part of this initial fall was directed in the x direction toward Earth, the burn propelled Webb into an orbit that's now tilted by about 33 degrees. The orbit isn't perfectly circular either, but rather follows an elliptical shape. As a result, Webb's distance from the L2 point varies between 250,000 kilometers and 832,000 kilometers. Now, for reference, the Moon's semi-major axis is about 400,000 kilometers. So Webb's orbit around L2 is enormous. This large orbit was chosen because it makes getting to L2 a lot easier. The farther something is from its orbital focus, the slower it moves and the less energy is required to maneuver. And that's why it only took a 5-minute burn and a 1.5 meter per second delta V. The large orbit also means that Webb will never drift into the shadows of the Earth or the Moon during its mission. However, larger orbits can permit stray light from the Earth or Moon to get past the sun shield and reach the primary or secondary mirrors. In addition, a larger orbit can reduce the number of communication opportunities with the deep space network. That's why Webb will have to change its orientation to keep stray light off the mirrors at all times throughout its orbit and schedule the communication downlinks accordingly. The Webb takes about 6 months to complete one orbit around L2. Although it sometimes flies out just a little bit past this point, the geometric center of the orbit is still centered on the L2 prime point on the Earth side. Remember, we don't want that ball right at the very middle of the saddle. That's why Webb will execute small station-keeping burns every now and then to maintain its orbit. Missions like Gaia only require 3 to 4 of these burns every year. But Webb will require much more frequent burns for a couple of reasons. For one, its sun shield is always feeling a torque from solar radiation pressure. Webb can counter this rotational force by spinning up its reaction wheels, but the solar radiation pressure is unrelenting, so the reaction wheels must increase their spin over time. Eventually, a station-keeping burn is required to rotate Webb back into place and let the wheels throttle back. Webb also changes its orientation as it points from one position to the other. All of these motions perturb Webb's orbit ever so slightly, requiring more station-keeping burns to maintain. And that's why Webb executes a burn once every 21 days. The exact timing and duration of those burns are calculated by the flight dynamics team at NASA's Goddard Space Flight Center. They'll do this by monitoring Webb's telemetry data and using ranging data from the Deep Space Network to pinpoint Webb's location and its motion at all times. They even take into account gravitational perturbations from the Moon and even the gravitational perturbations of the rest of the planets. So yeah, the flight dynamics team are really awesome, and they've got their work cut out for them over the next 20 years. And speaking of amazing teams, how about these amazing folks who are helping to keep Launchpad Astronomy going? And I'd like to welcome Marcel Barros, Steve C., Joe Curley, Timothy Fudge, Chris Gregory, Eric Johnson, Navanitha Krishna, Barry Stott, and Lucy Thursfield as my newest patrons. And
Okay, this is it.
Okay, thank you, John, for researching Lagrangian points, taking all the concepts and putting them together in a way that they logically flow from beginning to end, and giving that nice presentation video at the end by Christian Redding. And all your descriptions help make it easy to understand what's in the videos on YouTube. So for that, we'll open it up to questions and answers. Let's just look. I don't see anything in chat. We have a couple hands up. The first one is Al Aho. Would you please unmute yourself?
Well, thank you for a most fascinating presentation. My question is, the sun is moving at an enormous speed throughout the Milky Way galaxy. Does that motion affect these calculations?
I suspect that they might have looked into it, but I'm not sure that they included it in their calculations, because it is really an influence, gravitational influence of the object outside of the solar system that will have to be counted into the calculation. I don't think those are very significant. They're quite far. The sun is the most massive object in solar system. I can't think of another object outside of the solar system that will have appreciable, would exert appreciable force on the satellite. I mean, on a telescope.
That would be my guess too, but
yeah,
celestial mechanics is way beyond my pay grade.
Right. Thank you.
Okay, John Tomaszewski, would you please unmute yourself?
Yeah, great talk. I understood most of it, or some of it, I should say.
That's great.
Anyhow, L4 and L5, I believe that's where the Trojan asteroids hide out. Those are asteroids that have gotten caught and
Yes.
just stay in there. Is that true?
Yes. Actually, I think there was a great deal of research spent trying to find them. And I believe that recently they found one or two. They are not, their orbits are very kind of complicated. And they are probably not that easy to find. But yes, there are Trojans. I have a video which I will email it to you with one of the Trojans. Shows its trajectory I think it's called the horseshoe trajectory. It kind of goes around the L4, L5, comes back and goes the other way. And it's making sort of a mega shape type of trajectory.
Thank you.
Okay.
Okay, the next person is Rich Yeager. Would you please unmute yourself?
John, a truly amazing presentation. Thank you so much. I want to check my understanding of the kind of orbit that the telescope has. If I understood correctly, as it sort of goes around L2 prime, it actually winds up going on the other side of L2. That was the understanding that I got.
Yes.
And and so that brings to my mind the question of the problem, and understood from another part of the presentation that if it goes beyond L2, then all bets are off, because it's going to keep going further away.
Oblivion. Yes, that's right.
So how does that work together, that it can actually go past L2 but not be a problem?
Well, if you noticed, first of all, the orbit is around L2 prime, not L2. L2 prime is quite a bit closer to the Earth than the L2 is, and I think they have chosen L2 prime to be such that you will never run into a situation where it will orbit out, basically out of the solar system, essentially. I think that's quite a bit of an effort went into the orbit of the satellite, because you are sort of a teetering edge of possibly losing it if things don't go right. But I think the L2 prime is closer to the Earth, and even the orbit which is tilted, I think at the furthest point it's still close enough to the Earth to be able to bring it back.
Thank you.
Okay, the next person is Mark Edelman. Would you please unmute yourself?
Yeah, boy, I enjoyed this presentation so much. Just tremendous. I really like it. I'm going to rewatch it in the video. Just a little digression. There's one more Lagrangian point. It's the one on the opposite end of the opposite side of the Earth's orbit.
L3.
And you, of course, since it's behind the sun, that means we can never see it.
Right.
So is there, you might not have paid any attention to this, but have you read anything about any knowledge of what's there?
Actually, Lagrangian Point L3, which is the one that you're talking about, is the stuff where science fiction is being made.
Yeah.
Science fiction. This is where you could have aliens hiding behind the sun and never be found. As far as its usefulness for the astrophysics, or it's a very limited use, because it is essentially behind the sun. You have no good way of communicating with that point.
Well, the reason I asked is because, of course, we've had space probes that have gone far enough from Earth. They've orbited the sun separately, and so they have been able to see that point.
Yes, well.
And I've never read anything about any actual observations of that point.
I guess what you say, they were able to see that point. The point is just a space with nothing, with possibly something in it. I don't think they have seen anything at that point. But the L3 is a really great subject for this science fiction.
Yes.
Okay. The next person is Paul Tukey. Would you please unmute yourself?
Yeah, I've heard it said that, in talking about the Webb telescope, that, yeah, they'll run out of fuel and there's about 10 years it'll run. I don't know if that's the right number. Anyway, but there, at least notionally, there's a possibility of going up there and refueling it. And maybe they've actually included a valve on the outside so that if in the meantime we figure out how to do that, it might be possible. Is that true?
Yeah, that's true. They made provisions for possibly refueling the Webb telescope. It has, you can connect to it and resupply fuel. So they allowed for that possibility. But given that the Webb is 4 or 5 times further than the moon, it probably will have to be a mission without human being in it. So it will have to be automated. Right now, they don't have, I mean, they allow for that possibility, but I don't think they really think it's going to happen.
If you think about it, if the Webb turns out to be such an incredibly powerful instrument,
sure,
like with Hubble, you know, it had a projected lifetime, and it's been functioning well beyond that after they did the initial fix of the mirror. And you know, I mean, where would we be without all that extended lifetime? So maybe the Webb will turn out to be so valuable that people will say, well, we'll have to launch another one when the first one dies. But would it actually be cheaper and more effective to simply go up and refuel the one that's there?
The cost of the Webb is about $10 billion with 10-year lifetime. So it's, you know, you can do the math. It's $1 billion a year. Yes, it might be economically feasible that they will try to send a mission to refuel it. And they make provisions, but I don't think they really, right now they don't have the technology to do that.
Well, they don't have the budget for it. But...
And they don't have the budget for it. Right.
Okay. Is there anybody else that has any questions?
Well, okay, so I have one more
Sure.
question. You know, I mean, the thought of all these, every conceivable force that could cause a perturbation, and this is all run up into these calculations. So I have to ask, is relativity a consideration? Is that, do you think?
I think they had to use, I'm sure there is a fair amount of synchronization between the satellite and the stations of the Earth, because you really need a synchronization to establish where exactly is it in space. And that synchronization, I'm sure they are using relativity to make relativistic connections. Yes.
Yeah. And of course, they're also monitoring where it is, and then doing corrections in real time. So if there are other forces, like for instance, all of the planets, you say, well, you know, there are no closed form solutions to the multi-body problem. So
right,
presumably they're just, you know, rolling in the minor corrections that are needed.
Well, it does its corrections every few weeks. I think every 4 weeks, I believe.
Yeah.
Those are scheduled corrections. You have to keep in mind that the transit time between the Webb and the Earth is about 5 minutes. So if you try to do interactive corrections, you have to allow for the, it will never be truly interactive, because you may ask for correction. By the time you get the data back from the satellite, you may realize that the whole thing is, you know, screwed up and possibly gone off orbit to the Olympic.
One final question. How much risk is there up there at L2 from rogue space junk flying around?
Well, L2 by its nature is not a stable point. So you're not going to have a concentration of space junk around L2. So there is a risk, because there's always something can be flying through L2, but at least you're not going to have the problem with L4 or L5, which are stable points, is that you could actually have space junk colliding with you, with your spacecraft. At L2, because it's not a stable point, there's very little possibility something will hang around L2 and collide. There's possibility something will fly through L2, but not it will just short transit time. So the possibility is finite, but not very, very high.
Okay, we have another question from Mark Nadelman. Would you please unmute yourself?
Yeah, just a comment. Paul asked about relativity, and of course, our more ordinary satellites that orbit the Earth, like the GPS satellites, they do have to take into account relativity. And one reason for it is that because they're at a high altitude from the Earth, gravity is less and clocks run faster. So their clocks are not exactly synchronized with clocks on Earth. So that's one factor that's very important. And the other factor is that because they have when they have a high relative motion to a point on Earth, that also affects the clocks. So the GPS satellites regularly apply a formula to correct for that. Now, but it's all about relative velocities. And of course, at the L2 point, in the ideal case, there's no relative velocity. So that factor wouldn't be there. But since they have this gigantic orbit around that point, it's not a very fast orbit, but still it's big. And that means that the relative velocity to Earth is varying all the time. And that means that the clock on board the telescope will not synchronize with the clock on Earth. So that is definitely a factor. That's all.
Okay. Paul, you have another question? Unmute yourself.
It's not really a question, but more of an observation, which I think is pretty interesting and relevant here. You need fuel and thrusters so that you can change orbits and adjust orbits. So to push things in different directions, you need that. But interestingly, to do rotational changes in rotation, you don't need to burn fuel on a satellite or a space shot. And this is something that I learned because I was working with a team just before I retired from Telcordia, and we were actually doing some work with Raytheon and doing calculation of satellite orbits, believe it or not, for a totally different reason. And it's this, on a satellite, you will have things spinning on 3 axes, I guess, to stabilize. They don't use, these are gyroscopes, basically, I guess. And you can use them to adjust the angular rotation, but not just the rotation of the thing spinning in space, but to actually adjust the angle it's pointing. Because you've got something spinning on this axis, and if you make it a little bit faster for a bit, then the satellite itself has to adjust because of conservation of angular momentum. And then you spin it faster for a bit, and then it turns, and then you slow it back down, and you've actually managed to change the direction the thing is facing without burning any fuel. Of course, it does take energy, but on a satellite like this, you have energy which doesn't, that you collect on the solar panels. And although there's a little bit of pressure from the light, I guess, and you have to take that into account. But basically, the energy comes for free, and therefore rotational, corrections to the orientation, the rotational orientation, come for free in terms of fuel. Is that, check me if I'm wrong, but that's my understanding of things.
I think they do corrections periodically where they use fuel simply because of the solar pressure. The video talked about the solar pressure on the satellite. So they do burns to change the position of the satellite, and they have gyroscope or gyroscope-like type of machinery in there, which whose rotational speed is adjusted to depending how you want the satellite to face. But eventually, they have to, they keep adjusting, and at some point they have to use fuel to bring it back.
Yeah, I heard him say that, and my understanding of that is that you could keep, so if you just want to change your orientation a little bit, because you just want to point at a different star, for instance, star cluster or something like that, then you could do that without burning any fuel, because you could just spin your gyroscope in the opposite direction for a short time until it turned the satellite, and then you crank it back to the original rotational speed, and the net effect.
Right.
But what we're talking now is a continuous pressure from the asymmetric orientation of the solar panels, and therefore the difference in the force of light that builds up over time.
Right.
And so you would have to keep increasing the speed of your gyroscope to counteract
That's
that.
right.
And that gyroscope would have to go faster and faster. And eventually you'd burn some fuel in order to sort of reset that so you could reset that gyroscope back to zero, basically, and then and go from there.
I just checked with Alexa, and they said that she has 6 high-speed gyroscopes that constantly monitor and correct small movements.
Yeah.
Thank you, Alexa.
Interesting. Thank you, John. Can I thank your Alexa, or is that going to make her say something to me?
Still say something.
Hey, Alexa, what's the temperature outside?
Not loud enough. Alexa, what's the temperature?
Right
I
now,
just want to say
76 degrees
that
Fahrenheit.
the business with the
Tonight, expect
gyroscope
a low of 49
would be
degrees.
a very wonderful thing to hear about. John, you would be the perfect person, John Michejda, to be the perfect person to explain it to us, how a gyroscope can control the orientation of an orbiting object. Well, it could be very interesting indeed.
I'll put it on my list. Yes.
You know, I'm sure we all had the small gyroscopes that had a string on it, and you pull it and you get to do different things with it when we were kids.
Yeah.
I'd like to mention that the telescope was launched on Christmas Day last year, and they expected about 6 months before it gets before it's ready to take its pictures of its mission. And however, they seem to be slightly ahead of schedule. They've already shown some excellent results looking at their test star system, like nebula or galaxy or whatever it was. I don't remember exactly which one it was, but so we're looking to see some really excellent results in the next couple of months. So unless there are any other questions, I'd like to thank John for doing such a wonderful job with this challenging topic and helping explain everything so well.
Thank you.
And I hereby conclude the big meeting for today.